Dear students, welcome to my lectures on concept videos of chemical reaction engineering. Today we are going to learn about the effect of the different parameters on the concentration, which will in turn affect the rate of reaction and conversion for a given volume of any reactor. So let us go into the PPT. Imagine, so let me start the video with the result. Imagine any reaction that happens in any reactor depends on the rate. I mean, how fast and how slow the reaction is going to happen. It depends on the concentration. Why? Because if the concentration is increased, the rate can be increased. If rate can be increased, the conversion for a given volume of the reactor, which is less time, can be achieved. So for the batch systems, the concentration is represented by Ma by V, which is moles by volume. And the flow systems, the concentration is represented by molar flow rate divided by volumetric flow rate. So what today we're going to see, the effects which we are going to discuss is more for the reactions involving gas-phase systems, because the concentrations variations happens even more in case of gas-phase reactions and or the reactions involving the gas phase. And today we are going to see only the volume effects, only the volume effects. Let us go let us go. This is the concentration, which is defined by moles by volume. The volume, what you are seeing here, is affected by three different parameters, because volume in turn affects the concentration. Concentration in turn affect the rate of a reaction. And let us see, because we're discussing about the volume effects today, the volume is the parameters that affect the volume is three. One is moles, second is temperature, and pressure. Why? If the moles is increasing, volume will rise. That will concentration will get down, because volume is the denominator. Anything that rises in the volume will reduce the volume of the concentration of the reactant, thereby reducing the rate of reaction. And the temperature. See, if the temperature rises, volume rises. Of course, you can see from the ideal gas law, the volume, if you raise the temperature, the volume will rise. In turn, reduce the concentration and thereby reduce the rate. What is the effect of total pressure? If I raise the total pressure of the system, the volume will get reduced, thereby it will increase the concentration and increase the rate of a reaction. See, the overall effects of moles is decreasing the rate, and temperature will decrease the rate. Pressure, if you raise the pressure also, it won't decrease the rate. In fact, it increases the rate, because the pressure rises, the volume will get down, the rate will be higher. So these are the three different cases we are going to discuss with an example. In case of case one, we are talking about the moles which affect the volume. Case two, the temperature of the volume, and pressure, how the pressure will affect the volume. Let us go to the case one. This is the case one, which we are going to discuss effect of moles on volume, not one, it's on volume. Let us go back to your CRE basic concepts. Concentration is represented by moles by volume, and Na is equal to Na naught into 1 minus x. V volume is equal to initial volume into 1 plus epsilon into x. X is conversion into T by T0, P0 by P. T is the final temperature, T0 is the initial temperature, P0 is the initial pressure, P is the final pressure. So because we are discussing only the effect of moles, let us assume the initial temperature is equal to final temperature, which is isothermal. Initial pressure is equal to final pressure is equal to isobaric. So let us take the denominator term. And if you keep T by T0 and P0 by P equal to 1, your final volume is equal to initial volume into 1 plus epsilon into x. What is the epsilon? Epsilon means initial mole fraction of the A, because reactants, and what is the mole fraction of particular reactant in the mixture, into delta. What is delta? If you is your hypothetical reaction, 1 mole of A plus B by A moles of B gives rise to C by A moles of C plus D by A moles of D. And if you subtract the product moles minus the reactant moles, that give you the delta. So that is why you can incorporate delta here once you know the reaction. Let us take two examples to see the effect of moles. Example 1, which will give A is giving 2 moles. That means epsilon is positive. A is giving 2 moles. If we substitute 2 in place of here, minus product which is 1, 2 minus 1 is the delta equal to 1. And epsilon equal to initial mole fraction. If you consider, let us take a reaction in a piston and cylinder assembly. You take initial number of initial volume is 1 liter and mole fraction of A is also 1. Let us see some reaction is happening inside this particular piston and cylinder assembly, and A is becoming 1 mole of A giving 2 moles of B. In such cases, what happens to my volume? We are going to see now. So this is the reaction. Delta is equal to 2 minus 1. Epsilon is equal to this one by A0 into delta, which is 1, which is sigma, which is equal to 1. And what is my final volume is equal to V0 into 1 plus into epsilon into x. If I substitute value of delta and epsilon and V0, my initial volume is 1 liter, you are going to see the volume is equal to 2 now. That means if you conduct a reaction, at the end of a reaction, your volume will be double. You start with 1 liters, it will end with the 2 liters. Because of this particular reaction, A gives rise to 2B. What happens in such case? Because in such case, epsilon equal to 1, which is a positive. If epsilon increases, in such cases, the volume will increase. If the volume will increase, the concentration will get down and the rate will also be down. This is the example. Let us consider the another example where epsilon equal to less than 1. It gives assume a reaction A gives rise to 0.5 moles of B. By my same, the conditions are the same. Initial volume of the reactor and piston and cylinder assembly is 1 liter. Mole fraction is equal to 1. In such cases, delta is equal to 0.5. This minus 1 is equal to negative minus 0.5. Epsilon is equal to 1 into minus 0.5 minus 0.5. So my final volume, according to this equation, if you substitute the values, the volume is 0.5. That means if epsilon is negative, that means those reactions which will reduce the moles, that means 1 mole of A is giving half moles of B. In such cases, my volume will also get reduced. That means if you start a reaction which is of 1 liter, you are going to end up with 0.5 liters. That means if epsilon is decreasing, the volume will get decreased, then concentration will rise because of reduction. I mean, volume is getting decreased, I mean, automatically the denominator will get reduced. Denominator reduces, the numerator value will increase. So then the rate will automatically increase. And for schematics, see, if there is some random reactor, I'm going to take the balloon. I mean, I have filled a gas of A in the balloon and connected to the inlet of the reactor. I'm going to examine how much amount of volume that comes to the exit of the reactor. In such, if the cases where the epsilon is less than 1, that means A gives rise to 0.5 B. What I'm going to observe, I'm going to pump more amount of A. At the end, the less amount of B is getting converted. I mean, going to come out of the reactor. You can see the reaction in volume is going to take place because 1 mole is given 0.5 mole. Similarly, in such cases where epsilon is greater than 1, if you start, I mean, you are going to pump the A into the reactor. In the reactor, A is giving 2 moles of B. Of course, the volume is getting doubled because 1 mole of A is giving the 2 moles of B. That is how the moles is going to affect the volume, where in turn it affect the concentration and rate and conversions. Let us go to the case 2 now. Case 2, we are going to study the effect of temperature. And same equation we are going to get Ca is equal to Na by V, Na naught into 1 minus x, V naught into 1 plus into epsilon x into T by T naught into P naught by P. Now, in the present case, let us consider pressure is not changing, but the initial pressure is equal to final pressure. The ratio of P0 by P is equal to 1. In such cases, if I take this volume consideration, V equal to V0 into 1 plus into epsilon x into T by T0. Imagine consider reaction A gives rise to B. What is happening here? Epsilon equal to 0. Why? Because initial moles are equal to final moles, epsilon equal to 0, epsilon x is equal to 0. Finally, V equal to V0 into T by T0. T is my final temperature and T0 is my initial temperature. So imagine some reactions happening. I kept something in a reactor, 1 liter reactor. Suddenly I have raised the temperature. What is going to happen? Initial temperature is 273.15 Kelvin, and the final temperature is, I have raised it, I said double the temperature, 2 times the initial temperature. What happens? You know, V equal to, from this particular equation 1, and V equal to V0 into final temperature by initial temperature. What is happening here? My final volume is equal to 2 liters. That means if you start any reaction and increase the temperature, what happens? My volume is getting doubled. If my temperature is raised, the volume will rise. What happens to the concentration? Because the volume is at the bottom of the concentration, this particular concentration, and thereby the concentration will get reduced, rates will get reduced, automatically it affect the conversion. Imagine the other example. I have reduced the temperature now. For example, when final temperature is less than the initial temperature. Initial temperature is 273 Kelvin, and final temperature is half of this initial temperature. If I start my reaction at initial temperature here, which is at 1 liter, if you put up all the values in this particular equation number 1, which is V naught into final temperature divided by initial temperature, I'm going to get 0.5 liters. That means if you start a reaction at 1 liter, you try to reduce the temperature, half of the initial temperature, the volume is also reduced by half. So as you reduce the temperature, because of the reduction in volume, the concentration will rise because the volume is there at the denominator. So if the volume is reducing, the numerator value will rise. That means in case of, you can see half the temperature. That means the volume will reduces, the concentration will rise. So you can see the effect, positive effect. If the temperature rise, concentration will get down. If you lower the temperature, the concentration will rise. And schematically, we can see here, case 2. That means if I pump a gas through a balloon, trying to make some reaction happen, the exit temperature I have raised to, I have exit temperature, I have put a jacket, or here, if I raise the temperature of the final temperature of the gas, you can see the volume of the gas that is exiting the reactor will rise. The reverse will happen if I start my initial temperature, which is, higher, and if I end my end temperature is lower, of course, my volume of the gas B is getting reduced. Okay, this is what the effect of temperature. Let us see the effect of pressure. In case 3, the effect of pressure on the volume. Same example, same equation. Let us assume when you see the effect of pressure, let us make the temperature constant. The isothermal temperature, T by T0 equal to 1. So if you take the denominator value, this is what the denominator value. Once you substitute T by T0 equal to 1, the final volume is equal to V0 into 1 plus into epsilon x into P0 by P. Let us consider reaction A gives rise to B, which is happening in a cylinder piston assembly. Because A equal to B, 1 mole is giving 1 mole, epsilon equal to 0. The final equation, the final volume is equal to initial volume into initial pressure by final pressure. Let us example 1. What happens when my final pressure is greater than initial pressure? So let us consider I have some gas which is kept in the piston cylinder assembly, which is at the initial pressure of 1 atmosphere and initial volume of 1 liter. If I increase the pressure of my system to 2 atmosphere, what happens to my volume? Volume is equal to initial volume into initial pressure is 1, final pressure is 2. That means my final volume is equal to 0.5 liter. That means if I start with 1 liter volume, because of increasing pressure, by 2 atmosphere, my volume got reduced to 0.5 liter. That means the pressure will bring positive changes in that concentration. If I raise my pressure, volume will get down. If volume get down, the concentration will rise. In example 2, similarly, if I reduce my pressure, what happens? That is, I have started with my pressure 1 atmosphere and initial volume of the reactor, in the piston and cylinder assembly is 1 liter. And what happens if I reduce my pressure? That is, I have reduced my pressure to half of my initial pressure. My final volume will be E0 into P0 by P. That if you substitute all the values in this equation, you are going to get 2 liters. That means if you reduce the pressure, final pressure, the volume will rise. If volume will rise, automatically the concentration will get down. If you see here in the denominator, the volume is getting raised. Of course, if volume denominator is rising, the numerator value will get reduced. That is what you're going to see, the effect of pressure. And that is what here pictorial. There is some random reactor. If you're pumping some systems which is at the higher pressure, at the end you are maintaining lower pressure, automatically the volume will get reduced. Whatever the gases that comes out of the reactor, which comes at a lower volume, volumetric flow rates. And if my initial pressure is lower, I mean there is the initial pressure which is higher, and when the some reaction happens, when the products comes out at lower pressure, the volume of the products will rise. This is what the balloon system. I'm trying to give a pictorial representation of what we've been able to learn. What is the final takeaways? Rate depends on concentration. Concentration in turns depends on one of the parameters called, which is volume. Volume depends on moles, temperatures, and pressures. That means moles. When we talk about the moles, we talk about the epsilon. If it is greater than 1, then volume will rise, concentration gets down, the rate which gets down, the conversion for a given volume of the reactor at a given time will reduce. Temperature. If final temperature is greater than initial temperature, the volume will rise, the concentrations will get down, the rate will get down, the conversion will get down for a given volume of the reactor for a given time. The effect of pressure. If final pressure is greater than the initial pressure, if the pressure rise, the concentration rise, rate will increase, the conversion will, it will increase for a given volume at a given time of the reactor. So always keep in mind, today what we have discussed the effect of volume. So keep in mind what happens inside the reactor if some moles are, let us say, different moles are reacted to get different moles of the product. What is the initial pressure? What is the final pressure? What is the initial temperature and final temperature? All things makes a sense when it comes to the conversion and rates. So, thanks for your time. Hope we are going to meet with some new videos.